Ready? Yeah. Okay, so today is the fourth lecture in battery technology fundamentals, but this is the first one where we are introducing lithium-ion batteries, and I think for the rest of the semester we just want to stay with lithium-ion batteries. So today it'll just be an introduction, so I'll just go over the basic stuff, and there'll be a lot of other things to discuss, including a favorite topic, which is safety, so that'll come along the way. But this is such a big topic, we can just go bit by bit. So just to do a little bit of history, back in the 80s, if you recall, some of us old guys, we had that Walkman from Sony, and these portable devices came on board. Laptops in the 80s were no, we didn't have laptops in the 80s, so they came later and late in the 80s. But there were, Sony and others had a lot of portable devices, and they needed rechargeable batteries. So the problem back then was the rechargeable batteries were water-based. So they were like NiCad, nickel metal hydride, lead acid batteries. They were all water-based. So they had problems with energy density. They were heavy, they had large volume. So there was a real need for a rechargeable battery that was light with high capacity and low volume. So Sony was probably the first company that started serious research in this area of rechargeable batteries. So they took some of the smartest people and they moved them from their, let's say, acoustics, loudspeaker division into coming up with new batteries. So this was an extremely serious effort. And luckily, there was a professor, his name is Goodenough, but he was more than good enough. He actually, he spent his life on electrodes. So he too wanted to, he was working on batteries also, and his effort was to come up with a very high energy electrode. So problem with electrodes is, think of electrode as, let's say, a rod. It has a certain surface area, and that's all the surface area where you can store charge, right? You can have like last time we discussed lead acid batteries. So on the surface of the lead and the surface of lead oxide, you have reactions. But the reaction, the current is proportional to the area you have an electrode. So if you have an electrode like this pen, you only have very limited area, just the surface area, because the ions cannot go inside the pen. You want to increase the surface area hugely so that you can have more current density. So this professor Goodenough at Oxford, he came up with this positive electrode we'll discuss. And so that was the first major breakthrough that Sony could take advantage of. So let's see what the lithium-ion battery looks like physically. So physically, if you look at a battery today, a cell, not a battery. Battery consists of many cells. So the standard cell is called 18650. So that's the name of the cell. So 18 refers to 18 millimeters diameter of the cell. And this 650 refers to 65 millimeters length of the cell, and the zero might be 65.0. I don't know why they put the zero there. So inside the cell, you basically have a wrap. So you have this core, this wrapped material, that's the cell. So we will talk about this one. So let's see. So a cell has four main components. So first one is, let's say, the positive electrode. So in this class and any rechargeable discussion, we should not use the word cathode electrode or anode electrode. That's bad. We should only use the word positive and negative, and we'll discuss why. So second is negative electrode. So that's the second component. The third one, as we all know, is the electrolyte. So these are the three common components in batteries. In the case of lithium-ion batteries, Sony came up with a separator. So this was a great invention. Actually, you'll realize, we'll soon find out, all these four components required awesome inventions. Without them, we couldn't have lithium-ion batteries. So the first one, positive electrode. So let me draw a positive electrode. Let me draw it over here. So we begin with a very thin sheet of copper. So this sheet of copper is about, I would say, 60 millimeters wide, because it has to fit in that can, right? So it's 60 millimeters this way, and I don't know how long it is. Nobody tells me how long this sheet is, And on top of the sheet, they somehow, they don't tell us how, they coat a compound called lithium cobalt oxide. And this compound, this thickness of this coating is from 100 to 250 micrometers. So they take a copper, I should write this down. So this is copper foil. And this copper is only 10 micrometers thick. So I don't know how you can take a foil which is 10 micrometers thick and can put a coating of lithium cobalt oxide on it that is this thick. So physically, how do you do it? I'm clueless. So this lithium cobalt oxide, this was the discovery, invention of Professor Goodenough. Goodenough is spelled just as you know. And he's a German-born fellow. He's pretty old now. And from Germany, where he got his BS, he went to Lincoln Labs in Cambridge. From there, he went to Oxford University, became a professor there. At Oxford, don't ask me why, he worked on these oxides, and he came up with lithium cobalt oxide, which is absolutely key to lithium-ion batteries, and we'll discuss that in a few minutes. So that's great. So Sony, which is the inventor of lithium-ion batteries, and there's one Sony engineer who's key to this invention, and now the Sony Research Lab is named after him. So he actually works in a building with his name on the building. So how many IBMers have names on IBM buildings? Do we know? Watson, one, but he's not a scientist, He didn't invent anything but IBM. Okay, good. That's a big invention. Okay, so this is the positive electrode. It's not anode, it's not cathode, it's positive. Okay, good. So now let's go. Okay, we'll discuss more of this, but for the time being, let me move on to the negative electrode. So the negative electrode, let me draw it over here, is also a sheet of metal, but in this case, it's aluminum, Al for aluminum, and this too is 10 micrometers thick. 10 micrometers is 0.4 mils. By the way, the word mil is bad, it should say thou. It's 0.4 thousandth of an inch. So how do you handle a sheet which is 0.4 thou in mass production? And so this sheet is also long. I don't know how long. It has to be long enough that when you coil it and you get that little thing, that pellet or coil, it should fit in this 18 millimeter diameter, right? Okay, so this sheet is like this. And this too is coated with a material which they won't tell us the details on. And this material is, they call it modified graphite. So we'll discuss what is graphite in a few minutes. And this too is 10 to 250 micrometers thick. So we have now two foils which are both coated, one with lithium cobalt oxide, other one with modified graphite. And then you want to squeeze them together and roll them up to make this little packet. But before you do that, we don't want to short circuit them, right? So we put a wider sheet of, oh, my green doesn't work, so let me make it cross-hatched. So this sheet, also probably longer length, is put in between these, oh, let me mention this is negative electrode on this side. So this separator is put between the two electrodes. So let's call this the separator. And this is 20 to 30 micrometers thick. So you have these three things, and then you squeeze them together, you roll them, and you put them in this package. So far, so good, right? So the fourth one is, when you put it in the package, you pour in the electrolyte. And somehow the electrolyte fills the space. So this electrolyte is liquid, and it is propylene carbonate. It's organic solvent, so it's a solvent. It can dissolve things. And the thing it dissolves is salt, which is lithium, phosphorus, or F6, or is it phosphorus? Or is it something else? Let me check my notes. Let's see. Okay, it is LiPF6. So I was right over there, yeah. This is one of them. You can also have lithium boron F6. So this liquid is, has a density of about 1.2 grams per cc. Let's see, what else do we know about the liquid? It has a flash point. Oh yeah, flash point of 130 degrees centigrade. So let me stay on this electrolyte. So electrolyte is propylene carbonate. And what's the formula for propylene carbonate? Just for, I mean, we're not chemists, so anyway, we should know what it is. It's this. And I mentioned the flash point. So flash point is 132 degrees centigrade. And it has a freezing point which is low and boiling point that is high. But flash point, so what is flash point? So it took me some struggle to understand what flashpoint is, because I talked to some chemists and they confused me. So this is what flashpoint is. If I take a beaker of liquid, oh, before I go any further, alcohol, your gin and tonic contains what alcohol? It contains methanol. So the formula for methanol I haven't memorized. It's somewhere in my notes. But methanol has a flash point of, I think, about 16 degrees centigrade. In that ballpark, I could be wrong. So propylene carbonate has a flash point of 132. What you drink, if you drink straight 100% methanol, some of us are pretty crazy, flash point is 16 degrees. What is flash point? So flash point is this. If I take a liquid and I want to know what is this flash point, what I do is I do a lab experiment. I keep the liquid cool, let's say at 0 degrees centigrade. I apply a flame to it. If it doesn't ignite, flash point is higher. So I go to, let's say, 10 degrees centigrade. I again apply a flame and it doesn't ignite. Then I go to 16 degrees centigrade. I apply the flame, the liquid is is in flames. So 16 degrees is the flash point. For polypropylene, I have to go to 132 degrees centigrade temperature of the liquid and probably the air above for that liquid to flash. So polypropylene, while it's flammable, its flash point is pretty high. So we need so these are tidbits of information we'll use as we go along this course. So I thought this might be a minor diversion. So if you're making a flaming cocktail, you want to heat, so you want to have it above 16 degrees centigrade. So you can't have ice in your methanol, it won't catch fire. So this is a tidbit. You can impress your friends the next time that methanol is flammable above 16 degrees centigrade. Okay, so where do we go from here? Okay, so let's take this structure and see how we can make a battery out of it. So let me go there. Let me see if I missed something. Oh, a couple of things I missed. One is, okay, this battery, what is the voltage of the battery? So I looked up I Googled this battery, and it turns out the voltage is typically 3.7 volts. And its capacity is about 2.5 amp hours. And what does this 2.5 amp hours means? It means if I discharge the battery over a 20-hour period, then this is how many amp hours I will get. So you can take 2.5 amp hours, divide by 20. It gives you about what, 1.2 amps or something? No, 0.2 amps. So if I discharge the battery at so let's say 2.5 divided by 20 amp, if I discharge at that rate, it'll last for 20 hours. So at 20 hours, it'll provide 0.125 amperes of current. So that's the capacity of this battery. So how much does it cost? It costs 22 yens. So how much is 22 yens? 22 cents in American dollars. So it's so cheap these days, right? But just, so to go back into history, I was talking about Sony. So this technology, so Sony started working on this technology in 1981 or so, in that period. And they designated one fellow to head the team, whose name is now in the building. So by 2001, they had it commercialized. So they had a commercially available lithium-ion battery within about 10 years. And in 2011, this was a $11 billion business. So in 10 years, they came up with the main patents. And I think they had 2 patents which were key. And within 10 years, the business went up to 11 billion. I don't know what it is today, but it's expanding rapidly, right? So what about our friend Elon Musk? What did he do? So what he's doing is he's taking this cell and is building a massive factory, right? And his cell will be 20 micrometers in diameter, 20 millimeters in diameter, and 70 millimeters long. So he's modified it about 2 millimeters more in diameter and 5 millimeters more in size. So this is his Tesla cell that goes into his batteries. So he probably will make billions of these cells, you know. So that's that. So now that we get some idea of the structure, let's look at a little bit of the working part of it. So let's see how we can make this battery work. And so what I will do is, let me go on this side and draw the structure in a different way. So I'll draw the structure like this, like we've been doing before. So we'll say this is our aluminum, no, this is our copper. On top of that, we put our modified graphite. On this side, we have the aluminum, and on top of that, we put our lithium cobalt oxide. So this is lithium cobalt oxide. And this is electrolyte. So I've just changed the scale so we can look at the reactions that are going on. So we have, this is our negative electrode, this is a positive electrode. So when we assemble this battery, the cell, sorry, the question is there voltage? And the answer is, there is. So let's draw the voltage of, so this axis, horizontal axis, this point is discharge state. So battery is discharged here. At this point, it's fully charged. So this you can say is the state of charge. So we used the term before, state of charge. So we go from discharged to charged on the horizontal axis. And this axis is potential. So I'll explain what potential. So let's just draw a little line over here. And I want to, so I have another axis over here. And this refers, I'll call this goes from 1 to 0.5. And this X is the LiX-CO2. See, this is LiCO2. So this is cobalt oxide that contains some lithium. But the lithium can vary. So lithium can be high and low, but the cobalt oxide stays the same. So on this horizontal axis, I've written LiX-CO2. So I'm going to vary the X. I'm going to vary the lithium content on the x-axis. Similarly, I have another x-axis, which is, so this was X over here, this is Y, and this refers to LiYC6. In other words, this is carbon, this is C, but when a lithium ion enters over here, the lithium combines with 6 carbon. See over here, the lithium combines with 1 CO, 1 oxygen. On this side, the lithium ion, when it enters the carbon, it wants to associate with 6 carbon. So, okay, so now let's, with that knowledge, we have assembled the battery. So I put together this graphite on carbon, lithium, cobalt oxide, aluminum, and we packed it, we added the electrolyte. You know, the electrolyte is propylene carbonate, which is a liquid, and to that we add lithium, phosphorus, F6. So this is salt. So reason you need to add salt to the electrolyte, so to the solvent cannot conduct. It's just a liquid like water. So you need to add salt to the water to make the water conduct. So that's the salt we add. So this salt dissociates and gives us lithium ions. So it's the lithium ions that do the conduction. So at this point, we put our battery together, we made this package, and now we're saying, what is the voltage? So you could measure this voltage, that's easy to measure. But what I want to do over here, like we did last time, I want to measure the voltage across this electrode. Now, physically, I can't do that. But if I was a smart chemist in the lab, I can measure the voltage of the graphite with respect to a standard cell. So the standard cell, which we won't discuss today, is lithium ion. So basically take a lithium electrode and we measure the potential. So basically inside over here in my thought experiment, I put a lithium electrode and I measure the potential between lithium electrode and the graphite. And so that's the potential I'll draw over here. So this is a negative electrode potential. So that's the potential over here. And that potential, let's say, is at this point at time 0. Now similarly, I can plot the potential over here. Again, I can use a lithium standard cell and measure the potential. And this potential at the same state, let's say, is this. So this is a starting point. So this total is the potential across the battery. So if you measure this potential, you'll get that potential. So this is a brand new battery. So now what we do is we say we need to charge the battery. Because at this stage, the battery is useless. Because if you connect a resistor across the battery, let's say, if you do this, how much current will you get? You'll get 0 current. But yet there's a potential. So this is the open circuit potential. So how do we make this thing do work? How do we get energy from this battery? So for that, we have to charge the battery, right? So we charge the battery by, instead of putting a resistor, we put a charging source. So we make this side positive, that side negative. So we're pumping current in this direction. So that's the current we're pumping to charge the battery. So what happens if we do that? So we are applying a voltage. Probably this voltage will vary, right? So let's say it's 4 volts, I don't know, some high voltage like that. So current wants to go in this direction. So the thing that carries current in the electrolyte is the lithium ion. The lithium ion is there to begin with, because we took propylene carbonate, we put a salt in it. So there are lithium ions in this thing, in the electrolyte. So ions start moving this direction because the electric field across this, because of voltage across that. So these lithium ions, they enter the graphite, and the lithium ions become lithium. So the reaction on this side will be lithium ions plus electrons plus C6 will give you Li(C6). So each lithium ion that enters the electrode combines with electron, which is coming from this side, because current electron direction is opposite of current direction, right? So this one lithium ion combined with 6 carbon atoms, giving you lithium C6, and that's inside the volume. It's not just on the surface, it goes deep inside. So these lithium ions I'm drawing as dots, they populate the belly of the electrode. That's how you get the high heat charge density, not charge density, but capacity, charge capacity. Whereas in most electrodes prior to this point, you only have the surface as a reaction. So this is a huge invention. So this is Sony's massive contribution. It seems so simple, right? But prior to this is like 1985 or 84, right? This was not a known thing. So this is how the lithium ion, the negative electrode gets full of lithium ions, or now lithium atom, because once it enters this structure, it becomes, it combines with a C6, forms like a chemical bond, you know. What's happening on this side? So lithium ions are moving out, they have to move in from here. So on this side, the reaction is, let's see if I have space over here, maybe I can draw it over here. So the reaction over here will be that LiCOO2, we're starting with that, right? That gives you Li plus electrons plus COO2, so cobalt oxide. So on this side, the electrons are being removed. So this electron is removed, and the net result is this lithium cobalt oxide dissociates into lithium ion, into electron, and into COO2. So that's the reaction on this side. So this reaction and this reaction, they have a potential associated with them. So what is the potential? So in terms of chemistry, each reaction has the energy change, the Gibbs free energy. So this is Gibbs free energy. So for every reaction, there's a Gibbs free energy. And we know that delta G is equal to minus NFE. So this is the Gibbs free energy. N is the number of electrons taking part of the reaction. It's only 1. So N is equal to 1. F is Faraday's constant, which is 9500 coulombs, and we get the potential. So it's this potential that I'm plotting over here, and I get that value. For this reaction also, this is a delta G, and the delta G is minus NFE. So we get an E for that reaction, and that E potential is this. And the difference is the voltage across the electrode. So now what we're doing is we're charging the battery. So what are we doing? We are decreasing X. So X was 1 when we first started, right? For every COO2, we had a lithium. So X was 1. So because we're removing ions from lithium cobalt oxide, X is going to decrease from 1 to some low value. But at the same time, its potential goes up as we charge the battery. Now, in the case of so this is the positive electrode side. In the case of the negative electrode side, we are adding lithium ions to the graphite, so this potential will decrease. And as we keep charging, meaning we keep decreasing this X. Oh, by the way, the Y, I mentioned this axis is Y. The Y goes from about 0 to something like, let's say 0.8 or so, goes to a high number. So we're increasing the lithium ions here and we're decreasing them there. So this potential will keep going up like this, and this potential will go down, but it turns out it goes down in steps. And these steps we'll discuss later. They have to do with the structure of this graphite. But anyway, let's ignore that for the time being. So that's what the charging looks like. Now notice that before the potential, open circuit potential was this was on a new package. So this is first time charging, right? And this is the voltage across the battery. It is fully charged. Now why don't we go to higher region over here? This is like forbidden for various reasons we'll discuss later. So we don't want to remove all the lithium ions from the cobalt oxide. We want to leave more than half of them there. So we don't want to go beyond that, because then we damage the structure, the crystal structure of this. If you remove too many lithium ions, this structure collapses. So you want to stay above 0.5. And those details will go on later. So that's how we get to charge state. So at this point, the battery is charged. Now, there was one other big deal that made this lithium-ion battery successful, and that, as Sony discovered, was that when they did the charging for the first time, so this is first time charging, what happens is a strange thing happens. On this surface, something called SEI, which stands for solid electrolyte interface. It's like a membrane builds on the surface. So this membrane is because a reaction of electrolyte with with the graphite. We don't know the details, and that reaction builds this solid electrolyte interface. So all these terms, when you read papers on lithium-ion batteries, you'll come across them. So this is an amazing membrane. So this is like in our gut, we have membranes without which we can't live. So it turns out lithium-ion battery can also not live without this membrane. And I think Sony discovered this. So this membrane, what it does, amazingly, it lets the lithium ion go through. No problem, it's porous to lithium ion, but it won't let the electrolyte go through. Only the lithium ion can go through. It stops the electrolyte from entering because this electrolyte is nasty. It wants to attack the lithium and destroy it or damage it or make it something else. So the lithium ions can penetrate this solid electrolyte interface, but it won't let the electrolyte enter to come after the lithium. So lithium, once it enters the graphite, is protected from the electrolyte. And we know that the graphite and the electrolyte don't get along. So see, I use the word modified graphite. If this was just graphite, this won't work. The graphite and the electrolyte will attack each other and damage each other. But somehow there's something called modified graphite, which they don't tell us what it is, that protects, that doesn't allow the two to react in a destructive way. So this is the charging of the battery. So let me go and discuss the discharging. So I can do it on the same page. So what I will do is I will rub some of these things over here. So I'll put back my graphite and my lithium cobalt oxide. And this time, what we're doing is we're talking about discharging. So I replace the battery, the source of charging, with a load. So your load could be a laptop, load could be whatever, right? So now the current direction changes. We're no longer pumping current, we are draining current. Not draining, but yeah, I guess draining current. And the electrons will move in this direction. So now we're discharging. So now what happens is that this side is high voltage, this side is low voltage. So current flows like this. So electrons will flow in the opposite direction. So let's look at this side. So now current is flowing like this. So the lithium ions will flow in this direction. So which means that the Y, which is the concentration of lithium ions, is decreasing. So now let me use the blue pen. So we're starting off from here, fully charged state. So what happens is now we are removing the lithium ions from the graphite. This curve goes like this. So this is discharge. And this earlier curve was charge. So the voltage across this interface keeps on increasing, as shown by this blue curve over here. So what about on this side? On this side, we're pumping lithium ions into the lithium cobalt oxide. So its voltage will decrease like this. So this is discharge. And previously, we had talked about charging. So notice that when we so whatever we're doing, if we're removing lithium ions from something, its voltage goes up. When we're adding lithium ions to something, its voltage goes down. So lithium ions decrease the voltage of the electrode. And that has to do, all I can explain is, that has to do with this Gibbs free energy, that when lithium ions concentration is high, that when you look at this equation, the E value decreases. So now we are discharging, so the arrow should be changed to go in that direction, and this arrow goes in this direction. So during discharging, what is happening is the lithium ions get depleted over here. They get pushed back into the lithium cobalt oxide during this discharging. During charging, we go in the opposite direction. So just to recap, remember when we first built the battery, there were no lithium ions in the graphite, but then we charged by pumping lithium ions into the graphite. We remove them from the lithium cobalt oxide. We put them in this negative electrode, which is graphite. So we charge. So charging means the graphite is loaded with lithium ions. Discharging means these ions go back to where they came from, which is lithium cobalt oxide. So that's the basics of the battery technology. And one thing which is so important to mention, besides all these great inventions, another thing which is so amazing about lithium-ion batteries is there are no chemical reactions. See, when we did the lead-acid batteries, we talked about that one electrode is lead, one electrode is lead oxide, right? So when we discharge and when we built a brand new lead-acid battery, we had pure lead on one side and pure lead oxide on the other electrode. In between, we had 9 molar or 6 molar sulfuric acid, right? With a certain gravity, density, specific gravity. So, but when that lead acid battery discharges, the electrodes get coated with lead sulfate, right? So there's a big chemical reaction. Here, there is no chemical reaction, but there is some little bitty chemical reaction where you get this lithium cobalt oxide and lithium C6. This is not really a chemical reaction. This is like adsorption. So all that is happening is lithium ions are just going back and forth. So it's like there's no chemical reaction. So the lithium-ion batteries can be charged and recharged for like 50, 100 cycles and above without degradation, because there's no cell reaction, there's no chemical reaction in this cell. Now what we can do is we can dig into some more stuff. So let me talk about a topic which is basic to lithium-ion batteries, without which they won't work. And these terms, when you read papers on lithium-ion battery, you'll come across them. So our objective, long objectives at the end of the day, is we want our batteries to be safe, right? So whatever we do, we want our batteries to be safe, and we want to design a battery management system. So we'll be buying the batteries from Panasonic or Sony, but we have to learn how to use them, how to design the power supplies, to charge them, how do we discharge them. Yeah, we can buy the little chip from TI that'll do all that, but we should know something about it, right? We are a $90 billion company. We should know something with the technology we put on our machines. So that's the whole idea. So the main idea here is that we want to get educated enough to make a battery safe and to do good battery management, right? So when we do all that, we'll come across a term called intercalation. So this is a big term in lithium-ion batteries. So I've discussed that to some extent. And what intercalation is how do these lithium ions enter the graphite, and how do they enter the lithium cobalt oxide? How do they enter the two electrodes, right? So so this would be insertion of lithium ions into graphite and also into lithium cobalt oxide. But today I'll deal with graphite, and also removal of lithium ions from graphite and lithium cobalt oxide. So this is intercalation. How do these ions enter the electrodes and how are they removed from it? So to go there, let me just do a little bit of chemistry, which, by the way, I'm not. So what I will do is I will talk about the lithium atom the carbon atom because we're dealing with graphite. So before I deal with that, let me talk about simple chemistry. So suppose you have one proton. And then you have one electron orbiting this proton. So what does that give you? That is our hydrogen atom, right? Now, hydrogen atom is very angry. It's not happy atom. The reason it's not happy is this is the first shell. This is the first orbital. That's the only orbital hydrogen has. So atoms are angry when the shells are not full. So the first shell needs 2 electrons. So hydrogen is dying. It'll kill for this second electron. And that's why hydrogen forms water, because now you have this bond, and so hydrogen gets an electron from oxygen, and so they share these electrons. So oxygen, as a result, has full shell, hydrogen has full shell. So oxygen so gets happy, hydrogen gets happy. They're both very angry atoms because they both want electrons. So by sharing the electrons, the outer shells are satisfied. So that's hydrogen. The next element we have is what's called, so the next element has 2 protons and 2 neutrons in nucleus. So now the fact it has 2 protons, it also has 2 electrons. So this element is helium. So I was shocked to learn that helium was not discovered on Earth. Helium was discovered in the sun. And then we said, holy cow, we also got it on Earth. Isn't that weird? So that's where we discovered helium. So helium is happy element. It doesn't bother you. It won't do anything to you because it doesn't need anything from you. It's got 2 electrons in the orbit. So it's very happy. So helium is a happy element. Not like oxygen and hydrogen. Oxygen is so bad, pure oxygen can do you real harm, you know, because if you have grease and you have oxygen, psh, it'll ignite. And hydrogen, you know, is also, hydrogen is flammable and oxygen aids in the flame, right? Okay, now, so why are we doing all this? Because now I'm getting to our favorite element, which is lithium, right? So what is lithium? So lithium is 3 protons, 3 neutrons. So now you guessed right that it has 2 electrons in the first orbital and 1 electron in the second orbital, right? So it's got 3 electrons, 2 protons. And also, lithium is the lightest element in the solid state that exists, you know. So that's the advantage. So lithium is a light element, and and lithium, this reaction we've been talking about, so lithium plus electron giving you lithium, that has a delta G such that the potential is like -3 volts. So it's very, very negative potential. So that's important, because say if you take lithium and you take gold in a beaker and you put it in a liquid, then you'll get big potential across it. So one reason we get the 3.7 volts, we get this high voltage across the lithium-ion battery, the reason it gives us this high voltage is because lithium has a very negative potential. So I agree, there's a little bit of discontinuity between the electronic shell I was describing and how I got to this potential. Yeah, there's a disconnect here, but I just wanted to throw in the structure of lithium. And so the lithium ions, so lithium atom is small, right? Because it has only a few protons and neutrons. So that gives us an understanding of why it can enter graphite and leave graphite so easily. So I think at this point I'm going to stop. So next time I will talk about carbon atom, and then we'll discuss the graphite. What is graphite? How do you make graphite? Why is it that graphite allows lithium ions to enter it and stay there? So we'll start at that point next time. Yeah.
Do you know what the separator material is?
Oh yeah, that's a very good question. That's an important thing I'd really overlooked. So the separator is polyethylene. And this was another major invention of Sony. So Sony is all over here. So Sony invented the negative electrode. Sony invented the separator. So it turns out that the person whose name is on that Sony building, he had worked on loudspeaker membranes, the polymer membranes, for many years. So he was a membrane expert. So he came up with this polyethylene separator, and he made it such that it's porous. So it's got humongous porosity, microporosity. And that is very key, because what happens is, suppose there is some problem and you start getting leakage current. Actually, this electron flow current will flow in that direction. Let's say there's short circuit over here somehow, and you start getting heavy current. What will happen to the polyethylene? It'll melt. So polyethylene will melt, and the pores will close down, and the current will stop. So this is another key invention by Sony, the separator design. So it has a self-healing effect, that if somehow there is the localized current flowing, then the polyethylene will melt and the micropores will join up and it'll become impervious to the flow of the electrolyte ions. So by the way, Jeff and I did not decide on this question, but that's a good one. Thanks, Jeff.
Thank you.
Should we call it a day? Any questions? Thanks, guys. So we meet in 2 weeks. Next week will be a physical metallurgy lecture. Thanks.